Alright, so in the last video, I showed you how to make the biasing circuit. Let's open the library right now and you can see what we made last time. So this is what we made. The biasing test bias circuit, this guy. So in this video, I'm going to show you how to make the differential pair, and so to wrap up the op-amp circuit and the schematic and layout. And also I'm going to add a capacitor to it. So the designing the capacitor or understanding why the capacitor is improving the stability of the op-amp is not required for this class. If you are interested in learning how to do that, you can go to the CMOS book and find out the details about this topic. But we don't have time to work on that anymore, the AC analysis for the op-amp. So what we are going to do is I will teach you how to design schematic and layout of the op-amp, and you are going to just follow the steps, all the steps to make a capacitor, 10 picofarad capacitor. So get some concept about how to make a capacitor in the C5 technology, which is beneficial, and then just assemble them together to make a complete op-amp and put the op-amp into the pad frame and make it work. So this is what we all need to do for this project, for this course, and then we're done. So that's everything about the project for this Engineering 337 analog course. All right, so let's get started. So take a look at the op-amp I have. So that's the op-amp, that's the schematic. So if we make a snapshot, so usually I want to do this. If you have two monitors, you make a snapshot and move this guy to here, so you can directly just remake it. So now let's create a new cell, and the new cell we want to start from the schematic first, and the name of the new cell is test op-amp, and OK. So first of all, you need 22 by 2, 22 by 2 PMOS on the top, and they are how many you have? You have 2 of them, and then 10 by 2 NMOS transistors, and you have 6 of them. So let's find out the first one, and we're going to rotate it like this. Wait, PMOS, right? PMOS. Rotate it, and that's the first one, and we need the second one, and the second one needs to be mirrored. And the size is 22 by 2, same here. And the model is PMOS, right? PMOS, no set model. All right, move it here. Move this guy here. So that's the 2 PMOS current mirror load on the top of the differential pair. And NMOSes, how many do we have? We have 6 of them. They are in the same size, which is 10 by 2. So let's set up one, and we just copy and paste the first one into 6 of them. That's the first one, and we need the second one, and this one needs to be mirrored. And how many do we need? How many left? 3. So 4 left. 1, 2, and just do the same job here. And on the right side, which is a gain stage, we need a 220 by 2. It's a large transistor because we need a larger gain. The larger current is going to give you a larger gain. That's why, right? So this is 100. This is also 100 Okay, so now let's connect all of them together. This guy being shorted to here, and this guy to here. That's a current mirror load, so it's a gate drain connected transistor. So that's a differential pair, so these two need to be shorted together. And the gate, let's directly connect the gate to here, and then this point to the drain of the PMOS. And these two are the current mirror, the current source, right, at the bottom. And they need to be biased. So so we need a bias circuit, which is created, which is a biased test bias circuit. This guy is providing all these biasing voltages, and of course this one need to be connected before we do anything else. Let's get 3 ground nodes over here, and let's connect it to this, and this to this, and of course to here and to here. So it just shorted all these voltage nodes. I think because V bias P is on the top. No, V bias P is on the left. So we are not actually using this for these guys. So I prefer to go back and modify the positions of the 3 pins for this biasing circuit. It should be in here in the icon. So we want this guy to be on the left, and these 2 guys in the middle. All right. So now this guy, J, Ctrl J. All right. And now let's come back to this one. So this is definitely gonna bias this part, right? So this is a V bias 3. It's gonna bias this transistor, and this will directly bias this guy, and that's gain load. No, that's a gain stage, not gain load. There's no such a gain load thing exist. All right, so that's V out, and V out is being shorted to here. That's pretty much everything, and we need the 3 pins, V bias P, and V bias P need a pin, which is this guy, Ctrl J, and we select this part and we call it V bias P, and we need 1 input here, another, wait, no, we need a 1 input here, and we copy and paste, so we get another input here. So this input need to be called as VM, and this is need to be called as VP. And also we need a V out, literally, right? So call this as V out. So I'm going to add a capacitor later, not right now. So let's just try to make it work for now, and add the capacitor to the op-amp later. So that's everything about op-amp. It's pretty simple, right? And I will create same icon out of it. So let's do it. Create just right in this window and do a make icon view, and go to the icon view, trying to make it looks better. So grab all these pins. So that's the op-amp, the name of the op-amp, and I hope this one to be a triangle shape. Press Y on the keyboard and trying to make it into a triangle shape. I'm not sure if I can make it, but here it goes. Things fine. And that's a test op-amp. You need a VP, which is, V and VP, right? So V out should be here. So here is a V out pin. So we need this one to rotate like this, and then move everything to the output pin, and VM pick up the text and move it aside. Same here, and move these two guys over here. And V bias P should be a voltage. This is kind of special thing. When we are using the 741, the commercial product, we don't have this thing, right? The reason is we usually have a startup biasing circuit inside of the transistor, so don't need this. You don't need to bias it manually using an external resistor, but we don't have it here. We just want to make it easier to design, so I didn't include that startup circuit in here. So the icon is ready, schematic is ready, so the next step should be a layout view. I'm going to create a new view here and call it layout. So the name should be test op amp. So here's the op amp view, and you can see the op amp view on the schema on the tutorial actually. So let's just start one by one, because the right side. So I'm going to show you. All right, so here's a snapshot for the op amp and the biasing circuit. So this is the biasing circuit, and we can directly use it later. But now we need to design this part, right? You know that the gain stage has large transistors. So these guys are actually multiple transistors being combined together to make up that large one. So the way to understand is, it's because of the width right here is 220. It's not 22. So this is a 22 by 2, right? So we are not changing the length. So we just want to make a 10 times the width as regular PMOS over here in the previous stage. So the way to do that is, you can imagine what I did is you can make multiple 22 by 2 ones and combine them together to make up a 200. This is 220 by 2. And why is that? Why is this one is equivalent to the 200 by 2? So let's draw it on the pad, and let me show you why this makes sense. Okay, so the way we do this is, it's a pretty regular technology. When we are trying to make a, so for example, this one, that's the gate, right? And you have the N plus or P plus to metal contacts. So this is a 22 by 2, for example, and which means this is 22, right? And this is 2. So this is what the 22 by 2 means. So that's the length, because the electrons is going to travel in that direction inside the channel. So this is a channel. If I want to make it 220 by 2, so what I did is I stack 10 of them together. So for example, I have one, I have another one, and I combine them together with the same node. Okay, so here you need another side to have the node, the contact. Same here. So let's don't. It takes a lot of time to draw 220 by 2. For example, we want to make a 44 by 2. So how can we do that? If we short these two together, because they are sharing the same metal 1 to P plus contact, and these are the two gates, right? And so the way to do that is, so imagine that we have a metal, so metal here and a metal here, and we short them together, and then they combine to the middle, and here's the output. So this one, for example, this is source PMOS, okay? This is source, this is drain, and this is source, this is drain. So the way that works is, But definitely you need to short the gate together to make it one, right? Because they are just one transistor. So the gates should be shorted. So they only have one gate. So that's two pieces are being shorted. So it's only one gate. So the way you can imagine, you can think about this is why you combine two 22 by 2 together and you can make a 44 by 2 PMOS. Because I short these two terminals, I can imagine that it's something like I have two channels being shorted. If you rotate it, right? If you rotate this in this way, and you rotate this guy in this way, and you can gradually combine them like this, because this pin and this pin are shorted, right? So it doesn't matter if you split the middle one and move it, rotate it in that way, you are going to get something like this. So rotate this one to here, and you are getting this. Because the gate is still being shorted. And because this and this are being shorted, so you can directly short it. And this is the source, right? You rotate it in that way, split, just imagine you can break it in the middle. After you break it, you rotate it and combine like that. And that's your drain. And the drain is being shorted as well. So that's the drain. Why it's being shorted? Because originally they were just one node over here. So now it looks easier to understand because you didn't change the length at all, but you doubled the width of the transistor. So right here, this guy is equivalent to a 42 by 2 transistor. It's the same concept. When you combine 10 of them together, you are definitely getting a 220 by 2, right? It's the same concept. This is a pretty important technique when you are doing the layout. You need to do it if you are a computer engineering major or you are seeking for a computer digital, system concentration for engineering degree. You do need to do this because we are going to cover this a lot in the spring semester for the digital chip design course. So pay attention to that. So this is how that works. The same concept. If you have 10 of these ones together, and it's the same concept. You just combine them and put them in series like this. So there are two NMOS being stacked on the top of each other. So this is how you make this work. But you can see there are a lot of things here, but literally there are only 3 transistors. 1, 2, 3. Okay, because these ones are the tallest ones, so we probably want to make this one first, so we can fit whatever other ones being needed for this differential amplifier inside. Because this one defines the critical height for the entire thing. So let's start working on this one first. So let's turn on this layout view because the schematic view is done, and we need 10 22 by 2 PMOSes, right? So let's start with the PMOS. And this is 22 by 2. And this guy is definitely it's a PMOS model. All right, and now I need a P-act. So the P-act should be 22 as well. And I put one here. And I will not do the next one for now because I will copy and paste, and you will know. So you want to close the entire thing at the end. So do not do it now. Okay? And move it until you see error and move it back. Right? So it's done. This part is done. Copy, paste. See why I did that? And you want to pick up this entire thing. So when you hover your mouse on the top, if you see this square is not the contact. Keep in mind, it's a green color material inside. So you want to pick up the entire thing and connect here, and then move these two things together. You couldn't see that text anymore because it's not working here now because you have two combined together. But you want to do an F5 check. If it's clean, DRC clean, you are free to move forward. So now we have two. We need 10 of them, right? So now copy and paste. So now, and you have 4 now, right? You want to move this one to align with the top one and pick up all these guys and move it closer. So select this one, connect, and then move it closer and closer. And I think I can move it even closer. So one more step, and F5, no errors. And then you have 4 right now. Just count gates you have, 1, 2, 3, 4. If I copy that and paste, I'm gonna have 8 of them. So it's pretty close to 10. And so this can speed up your design process. Stop. F5, clean. So now I just pick up 2 of them, copy and paste. Move. All right. Connect. Move it. I think I can do it closer. You can see the gap is a little bit larger. F5, error. So I shouldn't do that. I5, still errors. What's the hell here? They're all here. It's too close. Seems like it's too close. I don't know. So let's Control Z, and I5, 8 errors. If I delete this guy and see I5, no errors, and then I'm gonna copy. I think this gap is a little bit larger than this one. Is it? Yeah, but I don't think that matters. That really matters. Does that matter? Why is it larger than that? I think I can move it closer, right? So move everything up by 1 step. I5 still clean. So now let's copy this two, paste, and select here, connect to here, and move it up. I5. So these guys are giving me errors. These two guys, interesting. I5 is clean. So I will do 4. I will do 4 again. I'm going to delete 2 of them. 1, 2, 3, 4, 5, 6, 7, 8. Oh, I have 8, so I'm going to, I will copy 4 of them. 1, 2, 3, 4. And I will place it here. Okay, and make the connection. And save. I5. So many errors. I'll just move it up. I think it's fine. Is it? I5 errors. Why is that? Definitely, I don't have any errors here, right? So this is clean. And even I do this, it's going to be clean as well. So if I copy this tool, you don't want to copy that. You want to copy this tool, right? And move so they're aligned. and connect, and then move. Is alright? I5. Why is that? So it's reporting that the space is too small. Do I have 10 here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I definitely have 10 here. Let's move it down a little bit and see if that will help. Anything here? I hope it will. I5, 5 errors. Still the very last one. See if I delete this one. If I delete it, do I still have errors? I still have errors. So it's over here. So the errors is here. Is that because I didn't make the connect? Yeah, I didn't connect it to there, which is weird. Why didn't do that? All right, I5 clean now, and I will do. I need one more. I know, so I'm gonna copy and paste this guy, and do this, and I will move it up. I think this is appropriate. So now it's DRC clean. And now I get 10 of the PMOSes. This takes longer time than I expect, but it's done. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 of them, which is right. And then NMOS. After the PMOS and NMOS. So NMOS we need 2 100 by 2, right? So this should be 10 by 2. And we select this guy and go to this. And wait, why is running a simulation? I should click here. Control I. This should be NMOS. I hope I did the PMOS thing here. Yes, I did. And I want to place this entire thing a little bit apart from the PMOS stack. And I will make a NMOS for now. So let's do an NACT. So NACT should be 10 for the width. And we put it here. And make the connection and move it closer, and until it let us not to do it. Okay, same here. On this guy, connect it and move it closer. All right. Remember, I don't actually need that one, so I'm gonna copy and paste this guy and make it closer, align it. And move it up. Okay, I think this is fine. F5, no errors. And copy and paste. And connect this thing to here and move it. And then move. I think they are evenly spaced, are they? I think they are. And then the last one, not the last one actually, we need a 2 by 2. We need 2 transistors as well. So this thing need to be shorted to here. Move up. Right? And we need this one, another 4. I know we don't need 4, we just need 2 more, but let's just do 4, and I'm going to delete 2 later on. All right. Okay, I5, no errors, great. So let's delete 2 of them. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great. So this is done. And we need another copy of it. Just put here. So probably they don't need to be very apart away from each other. So these are the 2 NMOSes as the PMOS, and we need an NWell on the top. So the size of the NWell I used, let's just check it. I think it's just pretty similar size to whatever I use over here. I'm going to just check that the distance here and make the same. So it's 128 and something like 15, 128 and 15. Let's just make 130 and 15 to put on the top as a top rail. And the P-well as the bottom rail is also 130 by 15. It's over here. And so now it's the time to make all these fingers. So the metal 1, you can imagine that we are trying to connect the metal 1. So that's the first metal 1 to here, and then to here. We are skipping every P plus over here, and finally we short all the P plus together to make them as a drain of the PMOS. So this guy need to be here and skip 1 and connect to the final VDD top rail, and the same to this guy, and the same to, I didn't make it good enough, I think, and same to this guy, and the same to this guy. Okay, so this part is done, and so that's a common source. We just short all the sources together. Now we short all the drains together. The drains here and here and here. So source, drain, gate. So definitely all the gates should be shorted together. No doubt on that. So I will just short these 2 gates here for now, and I'm going to short every single one to the line, to the bus, because polysilicon layer is at a very pretty bottom level, so it's not shorting to the metal 1. They're not in the same layer, so that's fine. If you see they are being cross-sectional view, they're not being shorted together. So that's source, that's the drain. Let's do I5 very quick, so no errors. So source, drain, and the drain is being connected to the drain of the first NMOS, right? So now let's draw it. I probably move this one closer so I can directly connect it to the drain of the this NMOS, and the same to here. It's not hurting to move it a little bit closer, and here to this node. All right, and it's the same concept, right? So that if I connect this guy, this is the drain to drain. So that's the drain. If that's the drain, this one has to be the drain as well. So it's gonna be shorted to this node, right? So in that case, this is the drain, and this is the drain. This is the drain. The reason that one, if that is drain, this has to be a drain, is we have to skip every other one to make all these ones to be the drain. So you can imagine that you are splitting all these transistors and rotate it and combine them together, right? We just explained that over here, right? If you forgot, you can come back here to see why this works. And so these are the drains, and we need all the source. I will do this and connect all these things to here. No, not that one. Skip one, and it should be this guy. Skip this guy, skip this guy. And I5 clean. So that's the drain, that's the source. And same to this one actually. You know what? I should copy everything here, so I don't need to redraw it. So drain, source, and to the ground. Okay, and the gate. So all the gate here should be shorted and being connected to V bias 3. So let's do that. Short all the gates together. For whatever reason, it looks like it's not vertical. I don't know why, but I think it should be vertical. It is vertical. Looks not. It's not vertical. I don't know. It should be fine. All right. The gates being shorted together. And to here, and it's waiting to be waiting to be shorted to V bias 3, and the same to these gates. These gates need to be shorted together as well. And then here, 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 and the gate. So this part needs to be shorted to V bias 4, and this gate need to be shorted to V out. So these are all these pins we need to connect to. So that's a V out, right? So these are all these ports, and that's gain stage only, but we still need a differential pair. And the differential pair, I think you can just feel free to use every single one. If I just copy this one. So that's a standard PMOS, and delete the metals. So that's one PMOS F5, no errors. So I need another top rail to be placed over here, and because it has 2 of them, so I need to get another one, and they need to be in the same line. I can check it real quick by shorting these gates together, but looks like they are not. We move up a little bit to make them in the same line. So now they're in the same line, and that's the 2 PMOS, and I need the 2 NMOSs as well. So I will reuse this NMOS. So we should delete that, delete this. So the NMOS is being reused. It's a differential pair. Another one here. Right, align them together. They should be aligned like this. All right, so these are 2 inputs for the differential pair, and we need another 4 of them for the current mirror. So go up and be a little bit up. And copy and paste. All right. So definitely this one, metal, double click and do not extend it. Do not extend it on either end. Same thing here, right? Neither end. And definitely you need a gate drain connector. So this one shorted to here, so it's getting a metal one to your drain. So we need to connect the drain from this one to here, this one to here, and this one definitely is a gate drain shorted transistor, and this one to here, this one to here, this one to here, this one to here. That's the easy part. And another thing you need to know is because these are the differential pairs, so that's a VS. So you want to short these two pins together. And these are the current mirrors. So you need to know what are these ones. And this one is actually being shorted to this guy because that's a V bias 3. And these two are being shorted together as well. And this is being shorted to V bias 4. And usually, I don't know. I think that's fine. Usually they don't want to make a really long polysilicon connection. So this from here to here is considered as a little bit too long. So let's do this. So let's use the metal one, trying to reduce the resistance and to reach to this point. Let's do not extend it. So here is V bias 3 by V bias 4. And these ones need to be shorted to the biasing circuit. And I'm gonna drag and drop this bias circuit layout symbol to this layout view so you can directly use it. Of course, these two NMOS, the source of these two NMOS should be grounded. And these are all grounds, you want to short them together. All right, so that's the output, right? Output of the differential pair, and we want to connect it to the gain stage. So this is how that works. If you don't want to do this, I think no, that's not good. So let's delete that one, use the metal one to connect it. No, you want to pick up a node like this, a metal one. All right. All right, so that's a differential pair, that's a gain stage, so that's a V out. Let's label that as V out. Let's make it larger, for example, 20. And so now let's grab the biasing circuit. I'm pretty sure they won't be in the same size, and you'll see why. Let's do it real quick. So that's the biasing circuit, right? So you can see that they are not exactly in the same size. So you probably want to make this longer so you can match the top rail. So what I will do is I will measure the length over here and then go to this biasing circuit's layout view and to change it over there. So now let's measure that first. This is 305. Okay. So now let's go back to the biasing circuit, and I will start from here, and let's make a 305. So it's about up there. So I need to zoom out a little bit, and now let's do it again. 305 is up there, so I need to select. Oh, so the ruler is gone. 305, and I will pick up this guy and go up, go up, go up until 305. All right, so this is pretty close right now. And go back to the ruler's mode and press escape, and you can get rid of that ruler. And now let's go back to the op-amp view, and they should be in the same height right now. Let's see if they are. Not exactly, but close, I think. I think I didn't measure the. Yeah, it's not ideal. Let's measure that. Let's measure the from the corner to the corner. From here to here. 301 actually. So now let's go back to the biasing circuit and make a 301 instead of 305. 301 actually is here. All right, so we want to move this, keep this lower. All right, perfect. So now let's come back to the op-amp circuit. So it's been updated already, and I just move it. I'm just trying to move it closer, and then short all this biasing node together. Then we are pretty much done for this part. So here's a node. I want to short it here, and that's this guy, right? And VBAS P should be shorted to. It's not biasing anything over here, but this VBAS 3 definitely is doing something. So this is how we connect that and pick up. You just do a left click and right click at the destination. It's going to directly do that connector for you. But this is too close. So sometimes the automatic method is not ideal. So you want to do it yourself sometimes. All right. So I5, 5 errors. Interesting. I don't think I should have any errors, but I do have it. VMVP. Yeah, we don't have VMVP yet, right? So VM and VP. So what I will do is I will connect the. So this is VP. This is VBAS P as a node, and I will make it larger. Let's do 20. So that's VBAS P, and we need VM. So this is VM. But the thing is, it's a poly. You want to make a super long poly. So let's convert it into a metal 2 layer. So that's metal 1, and we need a metal 1 to metal 2 connector. Right, and then run metal 2 to the left side as the input. So this node will be VM. And let's make it larger. 20. How long it's been since? Okay, it's already about 15 minutes. So I want to stop this. Let's get this done and we'll stop, right? Come to here. That's a metal 1 to metal 2 connector. We get a metal 1 and metal 2 being extended to the left side of the chip, so it's more convenient when you are connecting this one to the pad. All right, so these are all these ones I need to do a ground as well. And here's another thing, because all these pins are in metal 2, so I want to make it consistent. That will make metal 2 for all these pins. So that's VDD, right? And I will make a metal 2's node and connect to there, connect to here. No, go to metal 2. Connect this guy to here as a metal 2. Metal 2. It's not letting me to do a metal 2. Why is that? So I will do this and press C to change it to a metal 2 node. Wait, C. I want to change it to a metal 2 node. Done. No, I need to click change, I think. Metal 2 node, change. Okay. Oh, it's already changed. So metal 2 node, and because the width here is, what's the width for this one? 14. Let's make 14 here as well. And rotate it. So I'm going to directly connect this node to this metal 1. See? And then you pick up this node and you name it as VDD 20. So the same as the ground part. Copy this guy to here and connect it to here and make it wider. I will do this. Then V bias P as well. So you need this, and you need a node, and you need a metal 2. And you name it as V bias P 20. Okay, and finally V out. Same thing here. V out. Let's make a metal 2 node here and connect to here. So we directly name it as V out and make it 20. So that's pretty much everything for the layout of the chip. And you do need the well for this part as well. So let's do it. So you want to select this one, so you can select the well. A pure P well, a pure N well. So at the very beginning, let's do a measurement. It's 120 by like 160. So we need a N well is 120 by 160, so it should be a pure N well node, and which is 120 by 160. So let's rotate it, and I will put it here. But actually, you know what? You can make this one larger. It's not affecting anything. So let's make it 400. How about that? See if we can cover all the PMOS. We still cannot do that. I just want to cover all of them. Cover all of the PMOS. Let's make it longer and wider. So it's going to be 600 and 200. All right. So this is a lot better, I think. But this is a bit too large, but it's fine. I don't think that matters. So that's for the PMOS, and NMOS you need a P-well node. So remember what's the size of this guy? It's 600 200. So let's do 600 200. It's a bit too large, but it's not a big deal. It's not affecting anything, right? Let's buy 5. I get 5 ladders. What are they? So what's the error here? I5, 4 errors. So these 2 transistors is not working really well. I think it's because, see the metal is going inside. So I do not want to extend this guy. And the same here. So do not extend it. And save I5. So now it's clean. All right. So this is your the schematic. If I press L, and it even matches the schematic. So this is perfect. First time it's done, right? So see here, I5. If I do I5, no errors. If I do L, matches. So we're done for the op-amp. And the next step will be the capacitor, and we're going to create a capacitor on the right side, but not in the middle. So you can see you'll see the wipe side. So what I did in the tutorial, I did it 2 years ago. I put the capacitor in the middle. So you have to, disconnect the wires and extend it to this part and put a capacitor in the middle. So I will make it easier. I'm going to directly put a capacitor behind it, so I don't need to redo everything. I would directly put it after this VL. I just think that matters. And after that, we're going to place the entire op-amp and the inverter into the pad frame we created previously, and we're done. So be patient. This is really worth to do this, because this is not only a lab. This is also a part of the project, right? So if you complete everything, you are done with the labs and also the project, which is 10% of the entire grade. So be patient and be prepared to spend a little time on that. And also, I want to let you know that for the course, I won't have any lectures for the very last week. I planned to have the BJT transistor covered over here, but it's just such a rush. I don't want to do that anymore. So I just will give you time to complete the chip layout, right? I will record a final exam preview video to put it here. The link will be available in the next few days. And these ones, nothing. I will just put a link over here to link to this video and another video I'm going to create later on to wrap up the entire chip. So no new lectures anymore. And there will be a new homework over here. So homework 12 will be the very last homework assignments. And we may have a quiz somewhere if it's necessary for the current meter stuff and op-amps. But I will let you guys know, okay? So the purpose is to give you more time to work on the chip, get it done, since this is pretty important. All right, so this is everything about this video. It's almost 1 hour right now, and I will see you in the next video.